So on to our last lecture before exam one. So exam one is coming up and we'll cover through the end of this lecture. So all the stuff on the gas laws, colligative properties, phase diagrams, phase transitions, and now solubility and solutions. So I want to set the stage a bit here with a thought experiment. So what I have drawn here is we have a beaker of, let's say this is pure water, pure H2O, and these are sugar cubes. So it's the same two, right? So we're just going to use sucrose as the chemical for sugar here, and there's the structure. Now let's think about what we already know from last lecture about solubility. So think about the polarity of this molecule, and I don't expect you to already know the structure of this and how this all works, but just think about these oxygens and how polar they are, and in fact they're oxygens bonded to hydrogens, and so we can actually have hydrogen bonding going on there. Remember that hydrogen bonding is going to require either fluorine, oxygen, or nitrogen. Well, we have the oxygen available here and the hydrogen bonded to it, so we can have hydrogen bonding with this molecule, and obviously we can have hydrogen bonding with the water. So that seems to set up a good solubility system. So that's what we're going to look at here. Now the molar mass of sucrose is 342.3 grams per mole, right? So let's say that we have a 34.23 gram cube. Each of these cubes then is 0.1 mole of sucrose. All right, cool. All right, so if we start dropping cubes into this water, so I've got down here a point that's supposed to represent 0, 0. All right, so we start dropping cubes in, and what's going to happen? How many of these cubes could we dissolve in the water? Now, hydrogen bonding and hydrogen bonding, so this should be a really good situation for solubility, right? But I think from your previous experience, you probably know that this is not unlimited. Let's say that this water is at 25 C for right now. We're going to get into the temperature a bit later in the lecture, but let's just say at normal room temperature, you know there's a limit as to how much sugar you're going to be able to dissolve in this water, right? So if you you can stir it and you can get a little bit more, but okay. And so you get this, the more cubes you drop in, the higher the concentration. This is molarity over here. You should be able to calculate that at this point. So you get more and more dissolved until you reach that limit, and then we're going to get this plateau, right? So what you're doing is you're graphing molar concentration, moles per liter, versus whatever we want to put on this axis. We could put number of cubes or whatever, just how much we've added. So you get to a point where you add enough that you've reached the solubility limit, and then it doesn't matter if you add any more, it's just going to lie on the bottom of the beaker without dissolving. Okay, so our max solubility for sucrose in water turns out to be 6.1 molar. So now what I want to do is I want to compare that. So we still have sugar, sucrose, that same sugar molecule, right? So here's our very polar molecule capable of hydrogen bonding. But now our solvent, instead of water, here I've got a new beaker, and this solvent is going to be hexane. Now again, I don't expect you to understand the organic structure here, but I do expect you to be able to see that, look, there's no polarity to this. We define the carbon-hydrogen bond as non-polar covalent. Okay, cool. So there's nowhere in here that you have a polarity set up for this molecule, so we have a non-polar solvent. And in fact, beyond non-polar, certainly we have no chance for any hydrogen bonding. So I hope that at this point you would expect this to not be a great molecule to try to dissolve in a nonpolar solvent like this. So same setup with 0.1 moles per cube of sugar here, right? And so we're unlimited stirring here and unlimited time, but what's going to happen as you add cubes, you get absolutely nothing is a bad term I'm going to talk about in a little while, but you get next to no dissolved sugar in the hexane, because sugar is not a good molecule to try to dissolve in a nonpolar solvent. In fact, the max solubility is somewhere less than 0.001 molar. So very, very low solubility. So this concept of solubility is that even things that do have a good match with your solvent often have a maximum concentration that you can get to. Not always, we're going to talk about miscible stuff, but most solutes do have a maximum solubility, maximum amount that they can dissolve in a given solvent, and it is different for different solvents. All right, let's staple a few terms on this. So let's say we look up the solubility of a given solute, right? And when it's right at its maximum solubility, we call that a saturated solution. If it is less than that, we're going to call it an unsaturated solution. Those are fairly simple. Now, it sounds strange to say it has a maximum solubility, and also we're going to talk about a situation where it's more saturated than that. But that situation is called super saturated. So there are specific conditions. Consider the idea. We're here in the South, so consider the idea of sweet tea, right? You know that if you have cold water, you can't dissolve enough sugar in that to make a decent sweet tea. So what do? You heat the water up, right, to dissolve more water, to dissolve more sugar in it, and that works. Heating it up increases the solubility limit, so we can dissolve more sucrose in it. But then what happens? You cool it back down after, and so you have what's called a super saturated solution. And we'll talk about supersaturated. There's a link later to a video that gives a great demonstration of that. So there are several things that are going to affect solubility, and I think primarily I would say is the nature of the solute. So that polarity match, that hydrogen bonding match, those are going to be the main thing that determines solubility. But temperature can also be important. We're going to talk about different directions that temperature affects things. And then if you're dealing with a gas solute, you have to consider the partial pressure of that gas also. So I want to point out a new thing here. Okay, we just talked about how the sugar solubility increases with increasing temperature, right? All right, so let's look at some new things. So these things that I have listed here: methane, oxygen, carbon monoxide, nitrogen, helium. At the temperatures on this scale here, and these are degrees C, what do all these compounds have in common? Well, oxygen is a gas, right? Carbon monoxide, nitrogen, helium, methane, these are all gases in this temperature range, right? So what we're going to do is we're going to look at a water system, an H2O solvent, and we're going to talk about the solubilities of these. Now let's look at methane first. A very simple molecule, CH4. And if you look at what happens as so we're increasing temperature to the right here on the axis. And so if you look at methane's solubility is up here at, at 0 to 5C. But as you increase the temperature, the solubility of the methane actually decreases. And if you look at oxygen, a similar effect occurs. Carbon monoxide, a similar effect. Nitrogen, and helium. So you can kind of look at the idea that these are typical gas. This is typical of a lot of gas behavior, that things that are gases at this temperature range actually tend to decrease in solubility with increasing temperature. So they're inversely proportional. And so, of course, we have a constant that we've developed for this relationship. So we've got, if we know the partial pressure of a gas, we can compute the solubility of that gas dependent on pressure. This is called a Henry's law constant, and it is temperature specific, but you get at a certain temperature, this will be the constant that gives you the pressure function. Now, if you want to extend this a little bit, certainly Calc 3 is not required for this chemistry course, but if you've already been exposed to the multidimensional calculus, you can think of a surface and a gradient, and so you actually have a partial differential here. So you've got a derivative based on the pressure, and you've also got another derivative, another direction based on the temperature. You can think of it as a three-dimensional, at least, surface. And I wanted to point out, when you look up these constants, they're published in various places. Get a couple of them here on the screen, but just know that the individual researchers publishing these constants are looking at their system of interest, and you may have to do a lot of shenanigans to try to get it into units that are more usable for you. A remediation engineering text that I use a lot uses Henry's law constant in atmospheres times cubic meters per mole. And different ones have different things that you may have to tease back into units that you can use for the system that you're trying to calculate. So another of my little thought experiments here to try to demonstrate what's going on with this partial pressure increase. So if we think about a certain pressure represented by, that pressure is proportional to moles. So if we have a few gas molecules, they're bouncing around everywhere, and some of where they're bouncing around is trying to get into the solvent, right? So there'll be a certain tendency of these molecules to hit the surface of this solvent and try to go in. Now, if you increase the partial pressure, that implies more molecules hitting with more energy over a given unit time for that same surface. And so you get more dissolution of the gas into the solvent. All right, so we can look at another system also. We can think about liquids dissolving in other liquids. So we started out talking about solids, like the sugar cubes, dissolving in liquids. And then we talked about gases dissolving into liquids. But you could go in between. You could just do liquids dissolving in other liquids. And a term that comes up in that is miscibility. So we call two liquids miscible if they mix well. Ethanol, alcohol, and water, they do work well, and if you think about that, both of them are capable of hydrogen bonding. So it makes sense that they would interact well with their intermolecular forces, and they do. And similarly, gasoline and oil are similar enough. They're both non-polar. Be careful with that. Gasoline and oil are both mixtures, really, but for the most part, you can consider them just non-polar solvents. And so they mix in a full range of percentages. But then the opposite situation is where you have non-polar liquids like our gasoline and oil, and something polar like water. And a lot of times we will call this an immiscible system. And I think you are used to the idea that some oils will float on water. You get a phase separation here. Can be kind of complex, and we're going to talk about some of the complexity of it in a second. But so you get this nonpolar phase and this polar phase, and there's nothing magical about oil always floating on water or vice versa. It really is just a density function. You can have some oils that are more dense than the water, and the water will float on top of the oil. It's just the immiscibility is about them not mixing well. And if any of you have ever worked on much on diesel engines, this is a picture of the side of it's just not my diesel because mine is nowhere near this clean, but a fuel water separator, and here's an internal system of what's going on in there. So what's happening is, and diesel engines can't handle any water really getting into the cylinder like a gasoline engine can because of the much higher compression ratios. You'll break something trying to compress water like that. So you have to get the water out of the system. Well, basically what you're doing is you're using the immiscibility idea and dropping the water out at the bottom of this separator system here. So in addition to miscible or immiscible, you could have the idea of partially miscible liquids. Like here the example is bromine. So here we've got bromine liquid, and in here we've got water, and you mix the two and you get this dense bromine liquid phase, and then floating on top of it you get this water with bromine mixed into it phase. And if you analyze this bromine phase, you would find actually there's water mixed into this as well. So these are miscible, or well, we should say partially miscible, because they don't mix in all percentages. So here's the contrast. So you could have a 3% alcohol and water mixture. You could have a 50% alcohol in water mixture. You can even go further. I mean, it might makes sense to start talking about what the percentage of alcohol in your of water in your alcohol is at some point, right? But basically, you can run the full range from 0 to 100% or anything in between. And that's not really the case with partially miscible, with bromine and water. There is some percentage that you can mix in from both directions, but they don't really cross over. You can't really get like a 50-50 mixture of this one. It's not that soluble. It's more soluble than like a hexane in water, but it's not like an alcohol in water. It's somewhere in between. Now, especially for my sustainability and engineering type folks, so a thing I ran into in the environmental remediation work that I did is you get an idea that, well, benzene is not, we call it not soluble in water. Well, so that works, except that it could give an incorrect impression that it's not soluble means zero, and it's not truly zero. Even though it's not a good solvent system, you can dissolve a little bit of your benzene into an aqueous, a water phase, and that's how we get groundwater contamination, because you have a dissolved plume that works out from a contamination. So even though we call it not soluble, it does not mean zero. So be careful of that. You can get some solubility. So I wanted to circle back around and talk about temperature function with solids. So we saw that sometimes with gases, a lot of times with gases, increasing temperature actually decreases the solubility. But just to point out that your former experience, like with the sugar and water, is that most solids dissolving into liquids, not all, but most, are endothermic processes. And endothermic means that it requires an input of heat or energy in order to cause the reaction, or in order to facilitate, let's say, the reaction. So adding more heat favors product side. Well, so that implies then that an increase in temperature actually increases solubility. This is the case for most solid solutes in an aqueous system. Just like if you increase temperature, you increase the solubility of sugar. Works for salt too. This is a link for what they have. It's a really cool acetate solution. You've got a supersaturated sodium acetate solution. So remember that supersaturated means that, well, we decide this is the saturation limit, and then we've somehow gone beyond it. I suspect in this video the case is that they have used a heated acidic solution to increase the solubility, and then buffered the pH up so that it's less acidic, and so you've decreased the solubility overall, but all that stuff is sitting there ready to crystallize out. They hit it with a seed crystal, and it's a beautiful example of crystallization from a supersaturated solution. Go watch that if you're interested. I wanted to refer back to, don't worry about this up here, we're not going to do the online here, but I wanted to point out this, this idea that I might ask you about. It cycles back to those different concentration units that we talked about. So if you figure out the molarity with respect to calcium chloride, right? So I'm dissolving calcium chloride, so you'd figure out the moles of calcium chloride, and we dissolve it in the liter, so the moles divided by the liters gives us the molarity with respect to calcium chloride. But now look at questions 2 and 3, and I want you to make sure you understand what I'm asking here. So for every, so look at the stoichiometry here. Calcium chloride leads to, so 1 calcium chloride leads to 1 calcium 2 plus 2 chloride 2 minus, or 1 minuses, right? Because of the stoichiometry there, if you look at it, the molarity of the calcium ion is going to be the same answer as question 1, the molarity with respect to calcium chloride. However, question 3, the molarity of the chloride ion is going to be double that, because there are 2 chlorides that come off for every 1 calcium, or for every 1 calcium chloride that dissolves. And then finally, we're going to edge over and do some reality checks here. So so we can figure out the solubility of a thing, and we can figure out, this is called the Van Hoff factor, the I. So if you look at sodium chloride, right, then you expect a total ions dissolved to be 2 for sodium chloride, because if you dissolve 1 mole of sodium chloride, you would expect 1 mole of sodium ions. You would also expect 1 mole of chloride ions for 2 moles of total dissolved stuff. I'm using air quotes there with my stuff, right? Contrast that to sugar molecules. And then, so this sugar molecule here, your I is just 1, because remember that this is a covalently bonded molecule, unlike the ionic crystal of sodium chloride. This is covalently bonded, so it's not, you're not breaking individual carbons and hydrogens and oxygens off of this. This molecule is staying intact, and so what you're doing is you're dissolving a bunch of these individual sugar molecules. So if there's 1 mole of sugar dissolved, you would expect 1 mole of stuff, air quotes again, dissolved in your solution, right? So for calcium chloride, what we would expect the Van Hoff factor to be, well, for every 1 mole of calcium chloride, like in that previous slide, we had 1 mole of calcium, but we also had 2 moles of chloride. So we would expect the Van Hoff factor to be 3 in that case. Similarly, for the sodium phosphate here, right? So the phosphate part of this is where it can get a little, you've got to follow all the pieces. They're starting to build up here, right? Phosphate is one of our typical polyatomic anions, right? So we're going to call the PO4 part of this 3 minus. That part stays covalently bonded together. So the PO4 breaks off, and then each of the 3 sodiums breaks off. So I would expect my Van Hoff factor, if everything works nicely, to be 4, because we'll get, for every 1 mole of sodium phosphate, we would expect to get 3 moles of sodium, and also to get 1 mole of phosphate ions for a total of 4 moles of stuff. However, that's what our expected Van Hoff would be. And then we do some experiments, and it turns out that it doesn't match reality perfectly. So let's take HCl. All right, so we expect, if we dissolve this in water, this is a strong acid, so we expect all the H's to fall off and all the chlorides to fall off. So for every 1 mole of HCl, we would get 1 mole of H pluses. We would also get 1 mole of Cl minuses for a predicted I value of 2 moles of stuff, right? And when we measure it, we get 1.9, which is pretty close to our predicted value of 2. Similarly, for sodium chloride, we'd predict 2, and we get 1.9. But let's look here, right? So magnesium sulfate. So the sulfate is one of our polyatomics. So we would expect this for a mole of magnesium sulfate to generate a mole of magnesium, also a mole of sulfate. We would expect a Van Hoff value of 2. But when we measure it, it isn't 2. It's only 1.3. Magnesium chloride acts a little better. We expect 3, we get 2.7. Iron chloride. Iron chloride is another one where we expect 4, and then we get a moderate value of like 3.4. All right, so what's going on with this? So we look at this, and these 1.9s match the 2s pretty well, but this 1.3 does not match very well. So there must be some even more complicating factor that we're going to have to deal with. So what's going on? Well, so we think that what's going on is that you have these ion pairs forming in solution. So we say that the magnesium sulfate is ionic and completely dissolves to magnesium ions and sulfate ions. And that's the way that we write the chemical equations in Gen Chem. And then another course is coming for a lot of y'all called Quant, where we're going to have to deal with ion pairs, and so you can get various types of pairing. So for that sodium phosphate molecule that we were talking about, you could get all 3 sodiums break off individually, and so you get 3 sodiums floating around plus 1 phosphate for every sodium phosphate that you put in there. But you could also get a situation where one of the sodiums actually stays attached to the phosphate, or even 2 of the sodiums. Or you can get a situation where you have floating around a stuck together piece with 3 sodiums still attached to the phosphate. You can even go further and attach more things to shift over to a positive ion or negative if you want to go that way. So the situation is going to get a lot more complex. Now, this happens when you have a very concentrated solution usually. You get a lot of solute interaction effects like this. Not usually much of an issue for a very dilute solution, so it's good to work out a lot of your initial experiments in dilute systems and then work towards more concentrated to see if we can figure out what's going on. So this refers back to a slide we had where we showed dissolution of the KCl molecule, right? So we had a potassium fully solvated by water molecules, and we had chlorides fully solvated, and then here we have one in process being pulled off, and here's our crystal that has not dissolved yet. Okay, so that's the simpler situation. Now we're going to go to a more complex. Instead of just having an individual potassium, an individual chloride, we might have an ion pair here. So we have a chloride still attached to one potassium and solvated. Here we have similar, but we could also have these individual potassiums. We could have more than just one potassium attached or more than one chloride attached. So we could start to have odd pairing systems out here and other complex ions. And then those colligative properties, you start to adjust them using that Van Hoff factor, right? That you know that the delta T should be affected by the molal, that's moles per kilogram of solvent concentration, and in that K value that we'll use in lab, but and that gives you a simple delta TF or delta TB. But now we start to think of, well, this experimental value right here, this Van Hoff says that, oh, well, maybe they don't all break up like we thought they did. So an application of these processes, you can take what's called fractional crystallization systems. So you can look at a system of, let's say we've got a mixture of sodium chloride and potassium nitrate in an aqueous system here. Well, they crystallize or dissolve, those are opposite processes of each other. And so you can use this function, this temperature functionality, to try to separate these two mixtures. This was one of the things that was a breakthrough in our region in the south with saltpeter mining. KNO3 is saltpeter, and so you can separate it from other dissolved salts using this fractional crystallization idea. And you can even go the other direction with a partial crystallization. So you have, here's an example of, let's say this is a magma, right? And so you've got this magma that starts to differentiate, right? And so differentiate means that you get some, like copper here, copper poor sulfides down here, right? But then you get this orange here, this copper rich sulfide. And so I know orogeology is far beyond the scope of this course, but what this shows is one of the reasons it's important to you, because this gives us things like copper mines, and why we have some zones that are richer in copper, and that we can get things to make wires, to make your cell phones and all your other electronics, because we get this partial crystallization system. And so as you start to precipitate out, like let's say your sulfide and your iron crystals, your copper might stay in solution longer and precipitate out in a different zone of the ore body, basically concentrating your system this way.